Let R be the region bounded by the graph y equals natural log of x and the x-axis over the interval x between 1 and e to the 20th. Let V be the solid generated by revolving this region around the y-axis. Find the volume and set the integral to find the volume. Okay, so basically what I did is this is tricky when we get some different functions that we're used to. So I typed in y equals natural log of x to the normal two-dimensional Desmos graphing calculator. And and I typed in y equals 0. Why did I type in y equals 0? Well, because they said the y-axis, the x-axis, which is y equals 0. Are you aware of that? So this is the x-axis. I know you know what the x-axis is. And of course, this is the y-axis. Um, but if you want to get the x-axis, this will give you the x-axis typing in y is 0. Why? Because the x-axis is the line that goes through at a height of 0. You see, that is the x-axis. It's the x-axis is a line, isn't it? It's specifically the straight line that goes right through the y-axis at a height of 0. All the points on this line have a height of 0. They all have y coordinates equal to 0. It is the line that goes straight through the y-axis at a height of 0. That'll give you the x-axis. So when they said it's between that and the x-axis, I typed in that and y equals 0. All right. So then I got my region. And now the region goes on and on and on and on. So I'm gonna put a stop to it. This is the region right here. This is the R. Now it goes all the way to e to the 20th. Well, nobody's got time for that. I'm just gonna go right here and call that e to the 20th and just, ignore the rest of that. Right? So we're just going to call that e to the 20th just so I can get a feel for what's happening here. And so there's the region and right, would it help if I did this? This is the region and we're going to rotate that now um, around the y-axis. So it's going to start, sort of here and go like, that wasn't very good. It's going to start sort of here and go like that for a long while, right? And they're going to have that other straight line right here. And, it's going to sort of do that. I shouldn't have made that come down, but whatever. Good enough. And then, actually, I probably should have just stopped it right over here. Let's call that the stopping here. I'll just call it right here. Here's the stopping point. I know it doesn't look perfect, whatever, good enough. But that's what it's going to do, right? It's going to rotate like that, making a three-dimensional frisbee kind of shape, right? I want to find the volume of that shape. Set up the integral to find the volume of that shape. So how are we gonna do it to set up the integral to find the volume of that shape? Well, what I did is I went ahead and I did the three-dimensional Desmos calculator. And that was a little tricky to do because whenever you put it in, you're going to have to notice it wants g of y and f of y. That's something you're going to need to be getting used to if you're going into higher calculus and stuff. And that is when they say g of y, a function of y means x equals, right? F of y equals something means x equals something. So let me let that think sink in for just a second. So when they say that, sorry, I wrote that funny. When they say f of y equals something, that means x equals something, or g of y equals something. Same thing. In either case, that means get x alone as a function of y. X equals something in terms of y. Right? Because normally you go y equals 3x squared plus 2 is whatever. We normally have y, something in terms of x. But if they say, give me a function of y, they want y on the right side. That means x is on the left side, doesn't it? So, so when I look over at this calculator, it says f of y, g of y. That means they want a function of y. That they're really saying, what is x equal, please? What is x equal, please? Well, x equals e to the y here. Why? Why is it equal to the y? Well, you go back up to the original function, it was y equals natural log x. So if I take y equals natural log of x, how do I solve for x? Solve for x because I need to get x alone here. How do you do that? Well, do you remember there's a base of e there? Remember how to change from a log to an exponential? It's kind of a swish thing. This goes there and this goes there. It becomes e to the y is x. Remember, and then log drops off. Remember that? You take the base, you go there and swishes around. You can see it's right because if you took the ln of both sides here, you go right back because the element cancel the e, y would equal ln x. So this is the same thing with x alone as that is with y alone. So then that's why I wrote x equals e to the y. That's the same thing as y is natural log of x, but I got x alone. In other words, I made a function of y, g of y. Okay, now what did I do here? Well, the other x value should have been x to the e to the 20th, right? X goes between 1 and e to the 20th. We can't go e to the 20th. So I just did e because e to the 20th is just too big. It's just too big to see it on this three-dimensional calculator. Can't handle it. So I just want to get a look at a piece of it, see what it looks like. That's all I needed. So I just stopped it at regular e to the 1, in other words, instead of e to the 20th. So I put those in if you're interested, and I've made this 0 and 1. I just wanted a small look at it. And there's what I got. Got this frisbee kind of thing, dog bowl with the hole in the middle. I don't know. What do you call it? So there it is. I want to find the volume of that shape. Okay. So how do we find the volume of that shape? Well, I turned it around to the back side of it. See, this is the front side. See this is the x-axis, the y. I turned it around in the three-dimensional thing, and the back side's easier to look at. There's the x, there's the y. Now you can see the washers real clearly. There's the washer. So let's use that to set up our integral. So we know the volume of each washer. What's the volume of each washer? Well, it's pi capital R squared minus pi little r squared times the thickness, right? That's how you find the volume of a washer. You've got the top area, then times the thickness, right? You know what I mean? Um, in fact, let me just stick a room in here. There we go. So you know what I'm talking about, right? For a washer, we have a little circle and we have a big circle. And we want to find the volume of the washer. So you got to take the little radius r from the middle to the edge. And then you've got to take the big radius, capital R, that goes all the way to the outer circle. And because you're trying to find the area of the donut, the area of the washer, right? So you got to take the whole circle, all the area, that's the whole circle, minus subtract out the hole in the middle. That gives you just the washer, and then times the thickness, however thick that thing is, right? So it's like as we look at this washer here, here's his thickness. And notice his thickness is going in this direction, dy. So this thing is dy thick, right? Can we see it? Well, my pen is going to be far too big. Let me see if I can make it smaller. Whatever. So it's dy thick. Okay, it's dy thick. Okay, so now we got us. This is going to be what? So now pi, what's the big radius? Well, the big radius goes from here all the way out to there. That's the capital R, right? And then the little radius. Well, let's stick with that one. So that's hitting this line out here. That's hitting that line. It goes all the way to that line, doesn't it? And the small radius only goes right there. Here, let me do that better. Small radius only goes right there where it hits this curve. Let me write that one in. There's that curve. Now, what are those curves? Well, back to my graph, right? There's that red curve, and then there's that blue straight line. I'm going to put that blue straight line right? That's what we're talking about. And so this one here is the little inner radius, little r. Oops, so good. Now I see what I'm doing. Okay. Little r. So little r and big R, don't we? We have the inner radius of the washer and the outer radius of the washer. The outer radius of the washer goes all the way to that straight line, and the inner radius just hits the red curve thing. So yeah, so can you picture that? So that's what's happening here. So we can see that on the flat two-dimensional graph, right? If we're at any point, I'm going to draw these again. I'm going to do the inner radius, which goes from there to there. That's the little inner radius R. And then the outer radius goes all the way to there. Call that R for the outer radius. Goes all the way to e to the 20th, doesn't it? The outer radius. So you see in that? The outer radius goes all the way to e to the 20th. That's all the way to that blue line. That blue line is at x equals e to the 20th. It's not really, but it's where it's supposed to be because x is supposed to go all the way to e to the 20th, right? And the inner radius just goes to the equation y is natural log x, doesn't it? All right, so let's do it. So the capital R radius, e to the 20th, and then that's squared. Capital R is e to the 20th, right? Minus pi little radius. What's little radius? Well, the little radius, now careful, the little radius is the x value. So that's going to be x equals e to the y, right? Remember the trick we just did? It's this equation, but he has a base of e, doesn't he? He has a base of e. Remember how that works? You go boom, boom. So e to the y equals x. That's how you change from log form to exponential form. Remember that from pre-calc? The base is e to the y equals x. That's saying the same thing. You can see it's right. If you do ln on both sides, they would cancel. It'd be y equals ln x. Same thing. So we need the x value, right? The little r is the x value, which is e to the y. It's right. It's how far the little r right there is how far to the right. It's not how far up. It's not a y value. It's how far over, how far on the x-axis to hit this equation. So I had to solve for x in that equation, right? So I had to solve for x in that equation. So bring it down. That's little r. Little r is e to the y, and that's squared. And the thickness, as we already said, is dy. So that's e to the y. So the little r is e to the y. Okay, there we go. And then we just need to add that up. We need to integrate that. Need to sum up, BS, sum up all those disks from where to where. Well, we're going along the y-axis, aren't we? You can see it, right? We're going in the y direction. It's hard to it's hard to have room anymore in this thing. We're going in the y direction, right? They're stacking up in the y direction. We start at 0. Where do we end though? It's a little hard to see. Kind of hard to see even on this other diagram. Where do we end? How high up do we go? We're stacking from y equals 0 to y equals what? Well, um, basically, you're going to go from, make this bigger, there's so much on this now, from 0 to the top. So the bottom is right here, equals 0, and the top is right here. Top, bottom, we're integrating this way. So what is that top? Boom. It's that right there that hits at e to the 20th. So when x is e to the 20th, it's the y value. The top is the y value that hits e to the 20th. Well, how do you do that? Well, that's plugging e to the 20th into this. Y equals natural log e to the 20th, right? Let's plug that e to the 20th right in there for x, because that's what this is. That's this curve. It's this equation. Plug in e to the 20th. What happens? These cancel. Y is 20. Top is y is 20. So we're integrating from 0 to 20. From 0 to 20. And there we go. There's what it is, 0 to 20. A pi e to the 40th, they just multiplied those, minus pi, and they factor the pi in the front, e to the 2y. So there we go. Just as easy as that.